Hi everyone. In today's video, we are going to continue the end-to-end user plane training sessions where we had covered already three very important sessions about the RLC, PDCP layer, and TCP layer as well. We have went through very interesting details. I advise if you didn't watch it to go back and watch it from the playlist where you can find it in that channel. Today's video, we are going to continue with the training about the MAC layer. Particularly, we'll be speaking about part of the MAC layer, which is the HARQ, because HARQ will be related for whatever we have discussed before, and partially some of the scheduling, how scheduling is being done for the MAC layer for the things related to the HARQ in general. But in general, MAC layer needs many sessions. So today we'll be covering only the HARQ out of the MAC layer, which is related to whatever we had discussed in the previous sessions. So this will be the main content of today, as you can see here. Initially, we'll go through a high-level introduction about the MAC layer, what it do, as from high-level perspective. This shouldn't take more than 2 minutes. Then we'll be covering a lot of other details about the HARQ typical pipeline, some feature like soft combining, the timing of the uplink, and other features related to the multiplexing and spatial bundling and so on. And this ad hoc will be covered almost in between, except for the 4G versus 5G HARQ, which will be the end of this session. But whatever we're going to discuss today, this almost covering everything you need to know about 5G HARQ. So stay tuned and let's see what we have in the next slides. As I just mentioned, we'll be first starting with a high-level introduction about MAC layer function. As you can see from the MAC layer architecture in general, it's the very simplified one. It's consisting of the RLC layer on the top, which is having something called the logical channels. They call the channels carrying the RLC information as a logical channel. And in the bottom here, you can see that we have the physical layer, which have the transporter channels to start taking the data over the air interface. So the first functionality of the MAC layer, which is the logical channel prioritization, or in general, it's like working to link the logical channels into the transport channel. So whatever control plane or user plane data is coming from the logical channels will be mapped or multiplexed into one transport channel or even multiple transport channels by the MAC layers. MAC layer will do that through multiplexing logical channels into transport channels. This kind of things we can go in details for it, but in a different session. But just from high level perspective, it's about the mapping of the RAC layer logical channels into the physical layer transporter channel. This is the first functionality. The second one, it's about the multiplexing and demultiplexing, and this is more like it's more as written in the bottom left here. It's more about multiplexing data across multiple components. Like for example, in term of carrier aggregation, the carrier aggregation is mainly handled by the MAC layer. It's almost transparent for the other layer. So this is one of the main functionality as well. Also, there is multiple other procedures, as you can see here, related to the hierarchy transmission, timing advance, random access, and so on. And also the most important for the MAC as well is the scheduling. Like it's mainly responsible for allocating the air interface resources and also doing this kind of link adaptation, assigning resource blocks, MCS, and all this information which you might be aware about it. But again, to cover all this information, you need more than maybe 10 sessions and so on. So today we'll be mainly focusing about the HARQ part as highlighted here. And just to give you a very quick introduction about the HARQ, HARQ in general refer to the downlink transfer on the physical downlink shared channel or uplink transfer in the physical uplink shared channel. And with HARQ acknowledgement returned in general in either, if the data is downlink, it will be returned in either in physical uplink shared channel or in the physical uplink controller channel, PUCCH or PUSCH. This is about the HARQ in general. And HARQ in general used for the retransmission or data transfer, as I just mentioned. It's a mechanism will rapidly correct transmission error. Like if you have any transmission error, the HARQ will be responsible for rapidly correcting all these errors, which might be due to some noise or unpredictable channel variations in the air interface and so on. But again, if you watch the previous sessions, as you know, RLC already have a retransmission. So why you need two different layers of retransmission? One in the RLC, in the top layer, which is here, and one in the MAC layer, or the HARQ in general, which is part of the MAC layer. The reason actually for having two retransmission mechanisms on top of each other can be seen in the feedback signaling. For example, the HARQ in general, okay, provides fast retransmission due to errors in the feedback. If you have errors in the feedback, the HARQ can quickly have a feedback and can quickly try to correct the information and provide a very fast retransmission to try to correct the information. But the main problem about HARQ that sometimes not all the information can be corrected. So you might end up by HARQ failures or whatever. So that's why I need the RLC on top of the HARQ in case if you have a HARQ failures. So RLC will be needed as it ensures almost that you have error-free data delivery, but at the end the RLC is kind of slower, have a slower transmission compared to the HARQ. Okay, the RLC have slower transmission compared to the HARQ. So at the end, the combination or the combination of HARQ and RLC provides a perfect combination or an attractive combination of the small round trip time. You will have a round trip time because of the very fast HARQ and also reliable data delivery because of the RLC. And at the end, this would be benefiting the upper layer such as a TCP as we highlighted before. So this can be result in a very good combination and so on. So now let's move forward for the very important information in the next slides. This slide is kind of a theoretical part, more about theoretical, but to understand about the HARQ typical pipeline or the HARQ feedback loop. And it's very important to understand this kind of information because at the end, whenever you are going to discuss other things in detail, so if you have the high level understanding of how HARQ work in between the transmitter and the receiver within the HARQ entities between the transmitter and receiver, you will understand it. It will be easy for you to grasp all the information we're going to cover today. So if you look into the left figure, which is the transmitter side here, you can see initially it's consisting of different steps being happening within the HARQ itself. Okay, first of all, like initially the information bits or the original bits, or in other words, data is being transferred. So the HARQ layer will initially attach some additional bits to the original information or to original data or the information bits, which is called CRC. Like it will generate CRC. CRC, as if you know for sure, it's called cycling redundancy check, and this is usually adding extra bits here to be used by the receiver from the HARQ side, as it will check this CRC in case to find any errors. So if any errors, for example, it will reply to the transmitter with non-acknowledgement. If no errors, then that means that data is correct and no problem in the data, so it will reply with acknowledgement. So the CRC in general is used from the receiver side to do like kind of error detection, only error detection. So if you're having any problems, it can feedback with either acknowledgement or non-acknowledgement. Then the second step here, there is something called forward error correction, and it's like in the where the output from the CRC after the CRC added the bits, it will pass through this forward error correction encoder where it will add extra bits, as you can see here. But this time, the CRC was adding the bits for the receiver to check and try to detect. But this bits is adding for the receiver to be able to correct the bits, not only to detect, to correct if any errors. So this extra bits will be used by receiver to do like kind of error correction. And instead of directly asking for retransmission, at first will try to attempt to do a kind of error correction. And this is one of the main differences compared to the RLC. In RLC, once data have an error, it will be directly sending non-acknowledgement asking for a retransmission. But one of the main functionalities of the HARQ, it will have this kind of forward error correction. We will try to do the correction and try to recover the data before asking for retransmission. Then it would go through the interleaver and modulator. And this is like just modulator, for example, to as mentioned in the bottom left here, to start doing this kind of modulation, assigning the bits into QBSK or symbols, which is having a specific modulation, QBSK, 16 QAM, and for example, 64 QAM, and so on. Then it will move through the buffer. And for me, the buffer is very, very important to understand. Why do we have buffer in the transmitter? and buffer in the receiver. This is like one of the questions you need to ask for yourself and within the HARQ, because at the end, like once the transmitter send the data, it have to keep a copy from this data in its transmitter, waiting for acknowledgement from the receiver. If it's received the acknowledgement, it can flush or remove this data from the buffer. But otherwise, if it's received non-acknowledgement, so it will be able to use this data in the buffer to retransmit it again. Because if it's already moved before, for example, receiving any feedback, so it will not be able to do the retransmission. That's why it's need to keep a copy in the transmitter in order to be in the transmitter in order to be able to do the retransmission whenever it's required. So assuming the data now moved from to the buffer side, it will do like a reverse operation for all these kind of steps. But the most important, again, you might ask yourself, why do we have buffer combiner? Why would you have buffer in the receiver as well? Again, this will be explained in details in next slides, but at the end, the main differences between the HARQ and the RLC and MAC RLC in general, for in terms of retransmission, that whenever the HARQ receiver will request for a retransmission, it will still retain the first copy which is being received, and it will start doing something called soft combining for any new retransmission. It will just combine all the new retransmission on top of each other in order to do something which we're going in order to be able to decode the data, which we are going to explain how this is happening in the next slides. And for all the remaining, it will do just a reverse operation, as we just mentioned. That's it about the typical pipeline. Now let's move forward to see what we have more interesting information next slide. Okay, this is like actually I was just discussing in the previous slide about that the HARQ receiver is having a buffer, so it can keep the data in the buffer in case if retransmission required to start doing like a combining for each new transmission and so on. And actually here, just this slide is very high level. I'm not going to go in details here in the slide because I already have a separate slides for each of these types. But simply here, if you look into those figures and even the summary in the bottom left here, the HARQ in general, as we highlighted, it refers to the retransmission protocol. Okay, that receiver will check errors in the received data, and if any error detected, then the receivers will buffer and keep the data in the buffer, receiver buffer, and do request for a retransmission. Then the HARQ receiver will be able to do something called combining the data as we highlighted. But in general, there is two mechanisms the receiver is using to do kind of error, to be able to do this kind of combining. It's called at the end HARQ soft combining, to be able to successfully decode the data during the retransmission. Because one of the main questions asking, what is the use of retransmitting the data again and again? What we'll get, like if the user, let's say, already staying in a very bad radio condition and is not changing his place, what is the benefit of retransmitting? This is actually what we're going to explain for these two types of HARQ soft combining. So the main idea that the HARQ receiver will keep the data, and whenever it receives a new retransmission, it will start doing this kind of soft combining in two mechanisms, something called chase combining and incremental redundancy. We'll go through both of them to show what kind of benefit, how the receiver can get using this kind of types of soft combining types to be able to decode the data successfully. So let's move to the next slide to cover those two types in details. And I believe you will really understand a very important concept about HARQ transmission in general once you grasp this kind of information about these two types. So the first type we are going to cover here, it's about the chase combining, soft combining. It's called first type called the chase combining. If you look into we have different figures here. The one on the top right here, this is quoted from 5GNR and Boltzbach, and it's just very simple. If you look into the figure, if you zoom in first before going to the detailed one in the left figure, see here we have the first transmission, which is your initial transmission, which is including all your information bits, as it's called systematic bits. Systematic bits means all the information bits is being sent in the initial transmission. But this systematic bits, for sure, it will have something called parity bits, which is at the end, it's kind of redundant bits, which is used for error, for example, correction. This is including your coding rate and so on, like can use for error correction by the receiver, so you can correct the errors. So these bits are mainly used for error correction. In case if the initial transmission being failed, so there will be a second retransmission or a first retransmission or a second transmission. This would be like a retransmission. If you look into these two figures, the blue part is related to the systematic bits, and this one related to the redundancy bits or variety bits. You can see the second one is exactly carrying identical information compared to the first one. Exactly the same one is being sent here. So this will help the receiver to do kind of a combining of this data. So this is increasing the combined energy, as I will explain shortly. So the receiver might be able to successfully decode that data because he will have a better signal to noise ratio. So you will be able to further decode the data. So let's try to cover this from technical perspective, how this is happening. Okay, as you can see here, initially the information bits was being transmitted. Again, CRC was being added. Then you will have the channel coded bits, which is adding for this FEC. Then the data will be transmitted over the will be transmitted from the transmitter to receiver over the air interface. Then the receiver will receive the data. So initially, this was the initial transmission. So initially, the combined energy was E, and the effective coding rate was R. Okay, effective coding rate simply means the information bits, which is this one, data divided by the total bits. Just like how much redundancy bits being added here in terms of for error correction. So as you can see, the initial transmission being received by the receiver, but in this case, there was like an error being detected. So the receiver requested for a retransmission. So the first retransmission being done here, and as you can see here, in the first retransmission, once it's failed, it requested for second retransmission and so on. But as you can see here, the chase combining in general, each retransmission repeats the exact same information as mentioned before. The exact same information would be repeated, and the receiver will soft combining all the received signals. And actually, this is increasing something called combined energy. The combined energy over multiple transmission will be improving the signal to noise ratio. For example, your combined energy for the first data transmission was E. Now it become 2E. Now it become 3E at the end, and a higher, this can improve your signal to noise ratio, and at the end, higher signal to noise ratio can enhance the decoding reliability and making it easy in general for the receiver to correctly receive the original information or information bits. So this is how it comes. But if you look into this part here also, which is very important, the coding rate kept fixed all over the three iterations of the retransmission of the transmission. You have three transmissions, so at the very end, the coding rate was fixed. Only the combined energy was increasing. And actually, uh, as you can see, whenever we add additional data, this is actually the energy adds up. The energy adds up. So the more retransmission, the energy will add up. So the more probability that the receiver will be able to decode the data successfully. But since the the retransmission is almost carrying identical information to the initial transmitter. So this one from the receiver point of view is more simple and require a lower UE memory requirements compared to whatever we are going to discuss about the incremental redundancy. So in a very simple form, this the chase combining is the retransmission is identical. All the data is being retransmitted again, and the receiver will be gaining from identical of the additional information or the new copy from the information. It will increase its combined energy, so it will improve the signal to noise ratio. So accordingly, it might be able to successfully decode the data. Now let's move through the incremental redundancy to see what is the main differences, as you will notice in the next one. Okay, you can see here we have many different figures. I tried to cover all the figures from different books and even from different websites, just because sometimes you might see all these kind of figures and you'll like not maybe see it as a complicated stuff. Okay, so here there is three figures explaining that. Okay, the one on the left, the one in the middle, and the one on the right here. Okay, and this is quoted from two different books. So if you zoom in, the first one from 5GNR in Bullet's book, which is the one in the middle, all of them giving the same message, but let's go through one by one quickly. This one compared to the first one, which is chase combining, you can see the initial transmission containing systematic bits and some redundancy bits or variety bits. The second one, it's completely different. It's having more additional variety bits, many variety bits, almost no systematic bits, which is no information bits, just adding additional redundancy bits means it will be impacting your coding rate. It will have a lower coding rate because you have more redundancy bits. So this is like kind implicit link adaptation because it's doing like changing your coding rate, increasing the redundancy bits, so it will be more able to do like kind of successfully decoding the data. I will show this from technical perspective. The figure on the right, I will explain it once I explain the one which is in the left here for that part. Okay. Again, if you look into this figure, initially the information bits was being transmitted, then the cycle redundancy will be added, then the additional bits for the coding will be added as well, and this is like will be containing your coding rate will be calculated here once the FEC bits or the redundancy bits will be added, which is called parity bits. So the transmission again sent, it was being failed, so it requested a second a first retransmission. But look at very important thing here. Here there is a something called RV, redundancy version. In case of incremental redundancy, there will be something called RV, redundancy version, saying this is the first redundancy version. The first transmission usually will contain all your information bits, and in this particular scenario, it will contain a very small number of parity bits or redundancy bits. Why? Because at the end, if the user was able to achieve, let's assume user in a good radio condition was being able to successfully decode the first version, this means you have a less overhead in the first transmission, so you are getting maybe higher throughput. Okay. And secondly, if the transmission failed, so in this case, you will be adding additional redundancy bits, which is called variety bits, as we explained in the figure on top here. So if you look into here, the first, this is the transmitter was having like some of the variety bits or redundancy bits and the data here. Then again, here it changed everything. Assume now this is completely different version. Just like giving here some additional how say it, additional parity bits or the redundancy bits without any information about the systematic bits. Sometimes it can have, sometimes no. But assuming this scenario, it's just having additional redundancy bits. That's why it's called the redundancy version, for example, 1. Okay. The sequence actually should be different, but anyway, assume it's redundancy version 1. Then again, here, if you look into the combined energy, it was initially E, then it become 2E. So this is the same as we have seen in Chase combining. So this is one advantage. The second advantage here, it's lowering your coding rate. Once you are lowering coding rate because you're adding more redundancy bits, so you will have more bits as overhead, and this is redundancy bits will be able like to help you to correctly decode the data. Then it will do the same scenario for each of the additional redundancy bits. For each redundancy version, it will be adding more redundancy bits or variety bits. So this is increasing 2 factors here, as you can see. Your combined energy is increasing and your effective coding rate is reducing. Means you have more additional systematic bits because of each of these versions, just more containing redundancy bits. It doesn't, most of it will not contain information bits. It will just contain redundancy bits to help the receiver to be able to correct the information. So again, this is the main idea here, that it's increasing your combined energy for each of the new at the retransmission, same as the change combining, and at the same time it's reducing your coding rate. So accordingly, you will have more redundancy bits on top of your original information. So this can help the receiver to correct the data. Now let's explain this picture, okay, which is actually giving the same information, but to be able to understand when you see it anywhere in any documents or whatever. As you can see initially, this one, the blue line, was the first transmission. And if you look at the shaded gray one, shaded gray is the systematic bits, which is again the new information bits. So the first transmission used to cover all the information bits, and the remaining just after this gray part, just you can consider it as a redundancy bits. So majority is information bits, and a few of it was redundancy bits, or they call it sometimes parity bits. Okay, so once this one being transmitted, it was failed. So there is a non-acknowledgement being received. So the second retransmission, as you can see, the first one was RV0. The second one is starting from is called RV2. It starts from a sequence RV0, RV2, then RV3, then RV1, and then it repeats if you have more retransmission. So you can see the second one, the second green one here. It's all of it doesn't contain any systematic bits. It's just additional variety bits. No any information bits or no original data is not there. Just additional variety bits or redundancy bits, which is lowering your coding rate. So this can improve your the receiver to be able to correct the data. So again, we assume that the second transmission being failed, so there will be a third transmission. And if you look at the third transmission, half of it contains almost redundancy bits or parity bits, and the second half contains systematic bits or information bits. It can again be repeated, no problem with that. So this will be the third transmission. The fourth transmission here, as you can see, also again contain a very few bits, and the remaining is parity bits. Okay. See, there is just one theoretical part here. The RV version 0, it's contained this shaded information, as you can see, the systematic bits, because it contained all the systematic bits, so they called it self-decodable. Self-decodable, that the receiver can decode it by itself. It doesn't require any additional information to do the decoding. But all the others is non-self-decodable. It's just used on top of the original one to be able for the receiver to decode the data successfully. Okay, so at the very end, the HARQ soft combining in general, okay, implicitly reduce the data rate through retransmission. Okay, and it acting actually as link adaptation, and unlike it acting as implicit link, do implicit link adaptation, and this is unlike the explicit link adaptation, the normal link adaptation, which we know it's mainly relies on the channel estimates, as you know, for example, increasing the player, changing the MCS, player target, and so this kind of things called explicit link adaptation. And the HARQ do implicit link adaptation through reducing the effective, for example, coding rate and increasing the combined energy and so on. And actually, in general, this approach of the implicit link adaptation through the HARQ transmission actually outperform the explicit adaptation, which is, for example, reducing the MCS based on the target layer and so on. Why? Because adding redundancy bits, as he mentioned here, only when needed, making it more effective at any for the error correction. Okay, it's more effective, and also at any terminal speed, at any device speed, and so on. But anyway, the explicit link adaptation, which we know, the normal one, is still must or necessary, because at the end it's having minimizing delay. It's acting like in a proactive way, while this one waiting for the first to decode the data and so on. The other one just based on the some estimation for the channel condition, so it's having a better performance in terms of latency, and this is ensuring acceptable quality of service. But again, one of the drawbacks associated with the incremental redundancy in general, that this one having more complexity, because at the end, as you can see, it's doing additional functionalities, and this is increasing the UE memory requirement. Let's move forward, see what we have for more interesting information next slides. Before going to the next slides, I would like to clear a very also important concept about something called a HARQ process single versus multiple. SAW. I did a correction here because it's SAW, not SOW. And this is referring to SAW, something called stop and wait. Okay. And here we're going to explain about a very important concept called HARQ process. And this HARQ process already there in the 4G and it will there also in 3G. But it's important in general to understand what it means by HARQ process at one piece by single and stop and wait HARQ, as you mentioned here, single stop and wait, and versus multiple HARQ stop and wait, as highlighted here. If you look into the top right here, this is explaining the case if you have a single stop and wait. Okay, so you can see the transmitter, assuming it's channel B, assuming the downlink direction, send some data to the receiver. Okay, which is the red one. Assume this is the original transmission. Then the receiver will take some time, receiving processing time and the propagation delay until it send the acknowledgement in the uplink direction here, as you can see here. So actually, as you can see in the single stop and wait, the transmission or the sender will not send any new data until you receive an acknowledgement. So this means you will have idle slot being wasted, and in this case, the sender becomes inactive while waiting for the acknowledgement from the receiver. So the average speed will be relatively low compared to the multiple stop and wait, which we're going to explain now. In case of multiple stop and wait, as you can see in this figure, the sender first will send the data at the slot 0, then the second new data at the slot 1. It will keep sending all the data, and each one of those called HARQ process. And despite the feedback, it just keep the sending the data. You have up to something called 16 HARQ process. But this example, assuming HARQ process, each one of those HARQ process will have a specific ID to be able to receive it to identify this process, this transmission related to which HARQ process. And as you can see here, the transmitter will not wait for an acknowledgement for each of this one in order to start transmitting a new one. It just sending the process, and it will wait. So even if this one is failed, let's say assume the first one at HARQ process, let's say HARQ process one, you have the first transmitted packet here, it's being failed. It will not stop sending. It keeps sending until it reaches the maximum HARQ process number. In 5G, the maximum HARQ process is 16. This means you can send in 16 different TTI, 16 different transport block as an example, and you will wait for an acknowledgement for all of them. And you will start from, again, from, for example, HARQ process 1 or 0, let's assume starting from 0. In case of all of them is being acknowledged, it will be starting from the beginning. And for example, HARQ process 0, if it's being failed, okay, so the receiver already will receive this one in the DCI, downlink control information, telling him that this transport block related to HARQ process 0. So whenever he feedback as a non-acknowledgement, he will also inform the receiver that HARQ process 0 being failed, please retransmit it again. So this will avoid kind of a conflict, and this is called asynchronous HARQ, as we'll be explaining later on. So the main idea of here of having different HARQ processes to have this kind of multiple stop and wait, do multiple transmission, and even if some of them being failed in the middle, it's continue with others. And if some of being acknowledgement, it can again continue using the new like cleaned, or the one, for example, if one is being acknowledged as mentioned here, so the next one here, the one here, will be a new transmission. And if it's being failed as mentioned by the 01, this means this one will be a retransmission. But again, assume now we have 1, 2, 2 and 3 being merged, and 0, 1 being received, 4 and 5 being received. This means you will have packets may arrive out of order, okay, to the HARQ. But in any case, as we explained in the BDCP part, the BDCP can take the care of that, because at the very end, the BDCP will do the data reordering as we highlighted in the previous sessions. So the key takeaway here, that using multiple HARQ process, as we just mentioned, enable faster and more efficient communication by avoiding unnecessary waiting time. And the main difference is, as we explained in the very end, compared to the 4G. In 4G, the HARQ process was mean maximum 8. Now we have up to 16, because this allowing a higher data transmission, because at the end, the 5G speed is much higher than 4G. That's why we need additional HARQ processes and so on. But again, this is increasing the chance of having data packet may arrive out of order. Let's move forward and see what we have next. This is actually the same figure, but just quoted from different thing. But this is exactly the same as mentioned in the top left here. And the one here using Python, as you can see, just giving a quick simulation. Assume here you have your transmission time interval, TTI 0 up to 15 as an example. And you have HARQ processes 0 up to 7. And all of them is being transmitted in parallel. As you can see, the first one, even it's being failed and there is a retransmission ongoing, the remaining is still being sent and over different TTIs. Okay, so it will not wait for the acknowledgement for the other in order to stop continuing with the remaining HARQ processes or the remaining transmission. No, it will continue, and it will just once it's having this one successfully, it can reuse it now for a new data transmission. This is the main idea about that part. Now let's move for the new thing. Okay, actually, this is also a very new concept, a new concept also in 5G. Actually, as you can see here, also the top examples on the right here, this is like assuming there is one transport block being transmitted over the MAC layer, okay? And as you know, the transport block size might be sometimes very, very big, like, for example, not fitting whatever requirement we need. But at the end, the transmit block size as a maximum, it's having a maximum limit. For example, as I remember, it was 8,000 plus for the 8,000 plus, or minimum as 4,000. 8,000, 4,000, different, depend on the coding rate type and so on. So actually, one of the complexity of the channel coding or decoding in general, whenever you have a large packets or the packets is being increasing, the complexity can be limited actually. can be limited. Like for example, the decoder or the decoder from the receiver side, if it receives a very large packet or large packet as a transport block with the maximum size, this is increasing some kind of complexity. It might fail and so on. This is one of the things. The second, also assume that you have a transport block, as I mentioned, with 8,000 bits, and only one bits, or let's say 50 bits, or let's say 10% of the bits being filled, and the decoder received a complete transport block. So he will need to do the retransmission for the, he will request retransmission for the complete transport block, not only for the bits which is being filled. That's why the 5G introduced this concept which is called code block group. What it do, the MAC layer can do a segmentation to the trans block into small code blocks. You can see this CV called code block. For example, this one is divided into 8 code blocks. Each one of those will have a different size, and those code block now it will attach to each one of those. The green one is the CRC, cycling redundancy check. So the first of all, the receiver can do the error detection based on the transport block, or based, for example, in code block, as you can see, the small one here. But actually, the main problem about the code block only, if the transmitter assume that you divided this one into 8, the receiver, the transmitter divided the transport block into 8, this means the receiver will need to do send acknowledgement or non-acknowledgement message for each of those. So this will increase the overhead in the BUCH channel or BUCH and the uplink, because now instead of sending one ACK or NAC, he will send 8 ACK or NAC. And this is actually, it's a good in terms of that if only one code block is being failed, so this one, only one will be retransmission. So it goes in the retransmission because only the code blocks, small code blocks with error can be retransmitted. But in terms of feedback, still it's not that good, because it will again for the system capacity point of view, especially in the uplink, it will not be that good. That's why they came up with the code block group, which is actually, if you remember the specification, the code block group can be 2, 4, or 6, or 8. What it means by 2, 4, 6, or 8? This means that one code block group can consist of 4 code blocks, or 8, or 2. So in this example, I'm assuming that each code block having 2 code block, each code block group having 2 code block, as you can see here. So in this case, for example, the code block group 1 was fine, no errors. Same for 3 and 4. Only code block group 2 having one of them within it. Code block 3 was suffering from some errors, so it was being detected by the receiver. So the receiver will only requesting for a transmission only for this one, code block group 2. So in this case, it's sending only for acknowledgement, for example, and non-acknowledgement only for that part. So this only the one with being retransmitted. But there is some dependencies in that part. First of all, it needs specific UE capability, as I will be showing in the next slide. This information you should find in the new capability called, for example, CBG transition indication downlink, supported or not supported, and also flash indication. Also, the here from the network side of GNB side, also to require to support the feature itself through that. First of all, it will configure for the user the maximum code block group per transport block. For example, it will tell the user that you can this one, for example, will be combined into full code blocks. The one code block group equal to 4 or 8 or 6 or 2 and so on. And also it can ask the receiver to flush or remove whenever those is being approved. It will ask the transmitter to flush it or take it out of the buffer and so on. And at the end, this information is transferring through something called some indication called CBG, just to be able to the receiver to identify which one is related to which code block group ID. This will be explained also next. But just in summary, that instead of the transmitter to retransmit the complete transport block, it can just transport a small part out of it if this feature is being enabled, because at the end the receiver will be reporting the non-acknowledgement only for one code block group or 2 or 3. It depends on the errors. So this is will reduce your retransmission in general as a volume point of view. Now let's move forward. See, now next slide will just, I will show you how to check this kind of capability from the UE logs. Okay, this one is just showing that how to check the code block group from UE logs. As you can see here, initially in our capability one here, you will go through that physical parameter. As you can see under the UE capability information, you will find Under the PDCP or the CMAC, then the physical parameters. Under that part, you need to search for the information which is called CPG, trans indication downlink or flush indication. This one was not supporting for the device, while this one was supporting. So this one reporting to the network. I'm supporting the code block group retransmission. So you can now enable the feature if you would like to have it in your network. Now, this is one of the most important part about the HARQ, because from this you can estimate how much it requires from the HARQ or from the receiver to send the feedback, and also you can estimate how much time required for 5G to do the retransmission, because at the end 4G is different than the 4G in terms of retransmission. Time is not fixed. In 4G, it was almost fixed as a transmission or a feedback time. It was knowing when the UE is going to send the feedback. But in general, as you know, assuming now that you have the transmitter sending some data, so the receiver or the device in general require a defined uplink timing for acknowledgement transmission after the downlink reception. For example, the receiver need to know when he's supposed to send the acknowledgement or non-acknowledgement and the uplink. For example, if you're assuming that this is for downlink HARQ, so the receiver need to know what is the uplink HARQ timing. So there is actually two methods or two types of the uplink HARQ response or feedback. So the first one here, it's flexible. As I mentioned, 5G in general is flexible. Flexible means there is no fixed time to be used by the receiver to send the feedback. For example, let's assume in 4G before it was fixed. Meaning what? That he know that if he received it in the slot number 1, he should send the feedback after 3 slots, for example. This was fixed, like 3 symbols or 3 slots, you need to send the feedback after. In 5G, no, it can be 1, it can be 2, it can be 3, it can be 4, depend on the configuration, which I'm going to cover it in details in the next slide. So let's first see an example from the flexible uplink HARQ. I can NAC time it. So assuming now this one being the first one transmission at very slot, so he will receive a parameter called K1 telling him that the offset to send your feedback after 4 slots. For example, 1, 2, 3, 4. So you need to send it in the slot number 4 after the first one. So you will know that, okay, and now I need to send the feedback here after 4 slots from this starting point. So 1, 2, 3, 4. So you know once you receive this parameter. Then the second one here, it received again additional one, which is called 8. So it knows it will not send it in the first uplink chance. No, it needs to send it in the key one after 8 slots. For example, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And this is assuming slot configuration DD 4 to 1. Okay. Then again, for the last one here, it will again receive this parameter as key one equals 7. I will show you also a real example from the traces, how this can be done, how to map it, and so on. But again, this is the main differences compared to the 4G. The 4G, it was like in fixed timing. Here, because first of all, this is TDD, it cannot be fixed timing, and in 5G in general, it's flexible. So as you can see, sometimes it can be very fast, sometimes it can take a longer delay to send the feedback. And I will show you how to estimate what is the minimum and the maximum time requirement from the logs. So this is actually what it means by flexible. Flexible means that the acknowledgement or the feedback in general can be sent at any time defined by the network, and this information will be delivered to the UE in the RRC message and through the DCI information, as I will show in the next slide. The multiplexing uplink HARQ timing, this is still flexible, but just this means that, for example, you have 3 transmission here. This means all these 3 transmission can be multiplexed at the same uplink timing. For example, if you look into here, the D1, the first 3 transmission, all of them being multiplexed and sent at the same time. But there is some consideration from the GNB side, because it knows all of them is coming at the same time. This means all of them is transmitting at the uplink at the same time. So the GNB need to take care of the BCH resources to avoid a collision in the acknowledgement term of resources. For example, not to let them all of them use the BCH information or BCH frequencies. And this is like from the scheduling point of view, this is done through the BCH resource indicator for each of those users, or for each of this, for example, feedback being sent. It will assign one of 8 RRC configurations to tell them, please send it here or there, and so on, because at the end, all of them will be sending at the exact same time. So you need to avoid this kind of resource conflict and so on. And whenever you have this kind of multiplexing, many of the HARQ being acknowledgement being sent at the same time, this requires the different BCH format. For example, require BCH 2, 3, or 4 because BCH format 0, which is the normal one which is being used usually, can support maximum 2 HARQ acknowledgement at the same time. This is just a quick information about that part. Here, just the bottom left here, this is just showing the layer 3 parameters which can be identified. This one will be showing details in the next slide. But one very important information I need you to know about it as well, very, very important. It's actually about the UE processing time. You might hear about that before. That, for example, if the UE receives the information downlink, he needs some time to start processing the data. For example, let's assume the UE need 2 milliseconds. This means this one must be more than 2 milliseconds. So there should be like some kind of information known by the network and by the UE for the UE estimation time. For example, if you look into the standardized table here, bottom left here, you can see that the minimum baseline for the UE processing time, for example, he needs around 0.5 millisecond to start to be able to process. This means this K, for example, at this particular scenario, should be at least in terms of FDD can be one slot because at the end is 15 kilohertz, so it can be one slot. One slot will be 1 millisecond, so it can send directly in the next one, as an example. In the case of 30 kilohertz, it can be directly in the next one because it's open 6 millisecond, or it should be at least 2 slots because at the end the user requires 0.5 millisecond to process the data. And if you compare this to LTE Release 8, as you can see, this is a significant differences and improvement in 5G capabilities devices. The user used to have wait for 2 milliseconds to be able to process the data. So this means he will do the acknowledgement after maybe more than 2 milliseconds. And this is actually not good for the network latencies. And this is actually one of the additional in 5G compared to the 4G in terms of device. Now let's give a very good information from how you can get this information from a network to be able to estimate the acknowledgement time, and also you can even estimate the retransmission from this kind of information. And if you have a drive test logs, layer 3 messages, and also this information being seen, how you can correlate and know when the user will be receiving and when the user will be sending the acknowledgement for the downlink data and the uplink. Let's see next slide, which is very, very interesting. Okay, in this slide, actually, I give different information. First of all, in the previous slide, I forgot to highlight, but there is one parameter called downlink data to uplink acknowledgement, the one highlighted here in this area. Okay, this is telling the user like what is the time intervals he have to wait until he send the feedback. For example, after 4 slots, 5 slots, 2 slots, and like acknowledgement and so on. So actually, this is mapped into a specific table. So this is how we're going to explain here. How the user will know the timing of downlink. Assuming now in the bottom left, bottom down figure here, you have some transmission downlink, and this is your frame. Your frame is working as A2 from the user perspective. So whenever the user receives, for example, data at slot 3 or 4 or 5, you need to know he's going to send the feedback here or here or here and so on. So what will happen? Initially, there will be scheduling information being sent in the DCI format 1.1 in downlink, the downlink control information. As you can see, this contains a lot of information. The most important information for us for the meantime is, for example, this is my numerology, 30 kilohertz, fine. What I need, what is my HARQ process? This sending, for example, in which HARQ process ID, because at the end, whenever the user is going to communicate, he also need to communicate the acknowledgement and acknowledgement for a specific HARQ to avoid any confusion between the GNB and DB. So this information must be noted. Also NDI, this is also one very important information. If this one, for example, for the initial transmission was 0, then it's toggled to 1. This means that this is like to differentiate, to let the user know whether this is a new transmission or a retransmission. So for example, in this case, it was 0. This means this is a new transmission. It's not a retransmission. So in some cases, this one might indicate that this one is a retransmission to the user to let him know that this is not a new data. No, this HARQ process is just a retransmission. The most important is this one, PDCH HARQ feedback time indication, which is the same parameter here. For example, here, this one is consisting of 3 bits. Okay, so initially the user would be receiving. So assume here you have a slot 4, which is this one, in the bottom left here. And this information is 1, okay, which is mapped to coming as 3 zeros, okay, 3 zeros. 30 is telling him, please go and check this one against 3GBP defined table. This is information known by the UE. So he will check these 3 bits, all of them is 0. What he will do, he will first go and map this information to the 3GBP table. And you can see that in 3GBP table, defined this from first value till 8. So it's having 8 values here. So it's telling him that 3 zeros, this will be the value number, the first value provided by downlink data to uplink acknowledgement. For example, as I mentioned, this parameter will be delivered in the RRC. So in the RRC message on the left side here, you can see within under the downlink data to uplink, you have 1, 2, 3, 4, 5, 6, 7. So you have 7 values, okay? And like in sequence, as you can see here. So that till now, the UE doesn't know this slot 4 should be send the feedback when. So once he got this one, which is 30, he will go and check for 3GBP tables. He will find that 3 zeros is referring to the first value. It's telling him, take the first value. This will be your information to be sent in the uplink. How? Let's see. The first value here is saying 4. This means you need to send the uplink for slot 4 after 4 slots from slot 4. So now we can, let's see, slot 4 down here, it will count 4 slots. 1, 2, 3, 4. So the uplink acknowledgement should be sent in this particular area. If you look into here, it will be like that. Second one, if you look into it, for example, slot 5, which is the next one here, is telling him this will be at 110. So it will go against 3GBP tables for 110. This is telling him that this is the value number 7 in the RR serial configuration message. It will go here, it will tell him, okay, fine. This is value number 0 after 12 slots. This means slot 5 will send the feedback at the very end of the frame, as you can see. This is long delay here. So you can see this is 12, so it will count 12 slots. So it will know it will be sent, for example, in the spatial slot, which is the binding of downlink and uplink. And we repeat the same information, 010, coming at the third value, telling him go and take this one, 6. So slot 12 will send slot 12, which is here. It will send after 6, which will probably it will be the very end here. We'll map it here, then it will be sending at this one. 1, 2, 3, 4, 5, 6 here, as you can see. And the same for last one. It's again 30001. If you look into here, referring to the second value, so it will mean after 5 slots, it means slot 14 will send 1, 2, 3, 4. So again, it will be sending at the last one here, which is slot after 5 slots. It's 5 values, so 1, 2, 3, 4, and 5. This is how it goes. But what maybe it looks complicated, maybe you don't need all this information, but what you need to know that from the RRC message, you will know that the minimum time to send, for example, in this particular case, in case of your frame is 8 to 2, the minimum time, and you have 13 kilohertz, the minimum time to send the feedback is 2 milliseconds, right? 4 multiplied by 0.5, 2 milliseconds. And the maximum time is 6 milliseconds. So sometimes you only to send the feedback is 2 milliseconds. This means your retransmission can even take up to 4 milliseconds, and sometimes even up to 12 millisecond or 6 millisecond or 8 millisecond, because at the end, this is just to send the initial ACK or NAC for the initial packet. So assume that you got a 12. This means after 6 millisecond, 12 multiplied by 1.5. So this means you need 6 milliseconds just to send the feedback. So in this case, you're expecting to have even a delay in the retransmission and so on, because actually you have a long time to send the feedback. So this is, you can just indicate the time of that you require to send ACK and NAC messages in the uplink. And I believe this is very, very important in case if you want to calculate the retransmission time to do your designing for the timer and so on. Now let's move to the next, see what we have still. But before moving next, just to highlight the uplink acknowledgement in general. This is can be sent also through a PUCH, okay? But this is controlled through other parameter called key2. So probably this will not using most of the time. It can be used, but the most common one is PUCH, as we just explained here, and this is through parameter called K1, okay? As we just explained here. Now let's move next to see what we have. Okay, here I'm just giving a quick explanation about all the parameters within the downlink control information for your information. For example, the DCI, the previous table, if I go back here, you will find that you have multiple parameters here. In case if you are doing some analysis for some of downlink control information, you need to understand what these kind of parameters used for. For example, the slot, telling you what is your slot number, numerology, telling you it's 15 kilohertz, 13 kilohertz, and so on. And this is a frame number. For example, you have up to 1023 frames, so it will tell you what is your frame number. You usually should know what's the frame number, and this is search space related information. You have the carrier ID telling him whether you have a carrier aggregation not 1 or 2 and whatever, and the DCI information 1110 whatever, and also the RNTI, the radio network memory identifier. For example, C is used for usually for a specific scheduling, aggregation level, and this RPG bitmap just telling you how much resources in terms of RBs you have, and format ID, MCS, and I highlighted before NDI, new data indicator. This is just used to distinguish between the data being sent, whether this one NDI, whether it's being a new transmission or a retransmission in terms of HARQ and so on. And again, very, very important information related to the redundancy version. So you will know this is which version, redundancy 1, 2, 3, and so on. This is required for the incremental redundancy as incremental IR, incremental redundancy for the self-combining, as we explained in the previous slide. And the last one, which is telling you the value required, K value required to be mapped to 3GBP table, which is PDCH HARQ feedback, in order to be able to compute when the feedback is going to be sent. Then the last one just refer to some time domain and so on. This is in general the explanation for this information, but this is all the information. Again, some of them already explained, like the HARQ process, the IRV, and the feedback time, research resource indicator, telling you which frequency you're going to send the uplink. And this one is going to explain the next one, called downlink assignment index. I will explain this one, what is the use case of that one. And this is CBG transmission information in terms of if you have a code block transport block segmentation. So it needs to provide this kind of code block transmission status. For example, the user will tell you do use for HARQ transmission decision at the code block group level and so on. And this is telling about the flush, whether this user need to be cleared or not and so on. This is just information can be received within the same table to the user to be able to identify some of the information being highlighted early. Now let's move next to see what we have additional here. Okay, in the previous slide, we have discussed about the timing in the uplink. Okay, like what kind of time required by the UE to send the feedback in the uplink. Okay, now this one is just speaking about the multiplexing of HARQ acknowledgement. What it means by that. For example, the user need to know how many bits or need to use in the uplink to be able to send the feedback. So there is two types actually of the multiplexing of HARQ acknowledgement. Multiplexing means that different HARQ can be sent together and so on. Okay, so there is two types, something called static codebook, as mentioned above here, and dynamic codebooks. Actually, in general, it's three types, but the third one recently introduced. There is not too much information about it, but the most common one, which is currently used in majority of the network, would be the dynamic one. But I'm going to explain the differences between them. But first, what it means again by multiplex of HARQ acknowledgement. If you read here, that the HARQ acknowledgement codebook defines how HARQ acknowledgement and connect are sent from UE to GNB. For example, this codebook, which is this time, allows the UE to multiplex HARQ feedback across. For example, let's assume that you have two transport blocks. So you need to multiplex the information, or carrier aggregation, or different CBG retransmission. So you might need to send the feedback for all of them, as I will explain shortly. Okay. First of all, as you can see in this example, static, what is the difference between static and dynamic codebook? The static one, for example, assume that this is just a very simple high-level one. I will explain the details in the next slide as well for each one of those. But assume initially here there was some transmission and DTX, nothing being transmitted, this continuous transmission. So assume the data being sent slot here, slot 1, slot 0, slot 1, slot 2, nothing, and so on. Okay. So what it will do in the static feedback, static codebook, it just have a fixed number of bits. It will send the feedback either it's received transmission or not. What it means by that, for example, here it's received to TX transmission, so it will send here a UE will feedback with acknowledgement, and for both of them. So in case if the GNB even didn't transmit anything, because it's having a fixed number of resources, it will send also non-acknowledgement. For the GNB side, it knows there is nothing here, so it will ignore it. So this one is good, that will have a kind of alignment between the UE and GNB, BTS and GNB, because the user, even if there is nothing here, will still sending a feedback. So GNB will know, so this will not cause any conflict, as I will explain shortly. And here, for example, this transmission was being missed, so non-acknowledgement being sent, so This is again, BTS can link the feedback because the user is sending ACK or NAC for each and every single transmission or even discontinuous transmission. So in case if this one was not being sent as non-acknowledgement, okay, so the BTS might get confused because it will not know that next feedback is for which transmission. I will explain this one in details later, but it's just keep with me now. Here, just simply the static codebook send the feedback with a fixed size provided by RC message for each and every single transmission or even discontinuous transmission. So this will be able to BTS to maintain the relationship between the transmission and the acknowledgement. This will be easy for the GNB. The dynamic codebook actually that is giving more flexibility because at the end, for example, assume here there was nothing being transmitted. So in this case, you are wasting your resources to send a feedback here, even if there is nothing, right? So this is actually a job from this particular dynamic. Dynamic, in case if there is no transmission, it will not send anything. It will not send any like a feedback to save the resources. So this is kind of saving the uplink resources here. But now assume the same example here, the transmission being sent here, and this one was being missed. Then uh, so assuming this one was being sent here and this one was being missed. So because it's missed, it's nothing being received by the UE. So in this case, it will not send anything because this is the dynamic phase. Dynamic, it will not send any feedback to save the resources. So this means this transmission, there is no feedback being sent from the UE. So the next one transmission, the UE replied with acknowledgement. So the unit B will think, because this one there is no feedback for it, the unit B will think that this acknowledgement for this particular missed transmission, and this is might cause a conflict. And this is actually the gain of the static codebook, that because it's sending for every and each single transmission or even non-transmission, ACK or NAC, so it's very easy to align from the BTS to align the feedback. However, this one, yes, it's saving kind of resources on uplink, but this kind of missing feedback might cause this kind of conflict from the BTS side. It can lose the relationship between the transmission and acknowledgement, as happened in this scenario. However, there is a solution for that, which is called DAI. I will explain this one next slide as well, but just keep it in your mind. We have this static codebook and dynamic codebook, just both of them to decide whenever how the acknowledgement and non-acknowledgement, what is the resources using number of bits used by the uplink for the UE to be sending this kind of information, as we highlight in these two examples, and the dynamic in general giving a better resource utilization, like reducing the uplink feedback because it's reducing number of bits required to send a feedback in the uplink, but it can have some conflict, but this is already being solved with this DI, as I will explain next. And this is just explaining the main differences between semi-static codebook type 1 and dynamic codebook type 2. For example, this one size is fixed, as I mentioned. It has fixed number of bits to send the feedback. But again, this is introducing extra overhead, as mentioned here, because it even includes unused ACK and NAC for the DTX, for example. While size for the dynamics adaptive can be high or low, depending on the requirement, and flexibility is much higher, and it's having lower yield. Okay, this one having high reliability for sure, because sending feedback for each and every single slot, despite there is a data or not. This one having a lower, but however, this can be fixed, as I will explain in the next slide and so on. So the multiplexing capability, this is actually can almost you can see close to each other. However, dynamic is also still better. So this is the main differences between both of them. I'll explain again with some examples, quick examples, how this is working, especially for the dynamic codebook after solving this kind of problem. But there is also the dependencies from the UE. The UE showed supporting both of them. I'll show this, and also the network capabilities. Let's move for next to cover both of them. The semi-static was kind of doesn't look very clear from the previous example, so this one it would kind of make it more easy. Assume you have three carriers, okay, as from GNB side. There is a transmission from three carriers, as an example. And these three carriers will be sending the feedback in the BCH for the master carrier, in the first carrier. For example, was carrier from the top here. So assume the first carrier have one carrier with one transport block per slot. 1, 2, 3. I have 3 transport blocks. So you need to know when the acknowledgement is being sent for all of them. We know all of them would be sending here, but we need to know what kind of information we have. We need to know as information of bits and so on. And here also one carrier, this one having one carrier, but up to transport block. For example, the first one slot having one transport block, while this one having two transport block. In case you have two transport block, this means you need to send two acknowledgements, one for each transport block, okay? So it will have two acknowledgements. The last one, actually, it's having multiple CPG. This transport block was being segmented, so it needs to send even four acknowledgement each for one of each code block group, and four here. So if you look into this, the figure bottom here, this was the transmission from the unit B. From the U side, you have a fixed number of bits information. This is a like you can consider as a view search. So we have a fixed number of resources. So you know, for example, in the first one here, the information received for the to be reported the acknowledgement after 4 slots. So you know that you need to send acknowledgement and non-acknowledgement after first 1, 2, 3, 4. So you'll send it here. So this one will be sent. But for this particular area, there was nothing. So as you can see, this one, as mentioned, an N. There is no scheduling here happening. But still, in the same time, this one will be used as number of bits. Even it's not supposed to be used because there is no transmission, but because of the static, as I mentioned before, it have to send the feedback anyway. So because no transmission here, so this one will be considered as non-acknowledgement here. It will send non-acknowledgement. In the case of dynamic, as we explained, this one will be empty. There will be no information, so it will save some of the BUCH resources on uplink. And it will be repeat the same. For example, here one carrier was up to 2. So the first one will be need only one acknowledgement. You can see there is 2 rows here because you have here 2 transport blocks. So you need to send 2 acknowledgements. So you have 2 rows here. But again, all the N will be sending again a feedback. So this is increasing the BUCH resources. So this impacts your capacity point of view. The third one, for example, here, again, having 4. So it needs to send 4 acknowledgement for the first one. Second one, nothing. So again, it will send 4 non-acknowledgement, increasing your resources. Third one, 4 acknowledgement. And here there is nothing. It will send 4 non-acknowledgement. So as you can see here, as alignment for the feedback between JNB and DE, it's very good because JNB is receiving, it can it have no conflict between which one being acknowledged or non-acknowledged for the transmitted slots or data. But at the same time, from the network perspective, this is not good for the BUCH resources because this is impacting your capacity point of view. And this is where we're going to explain more in more details the dynamic one. We already explained it, but we explain what is the solution to solve this kind of conflict and whenever it's there, received, and so on. So again, from the advantage point of view from the semi-static codebook, that it's predictable and robust because it's having fixed size, feedback structure as shown here. And this ensures the network always knows where to expect the HARQ responses, okay? And it's having a fixed size and even no data received, but the main, again, disadvantage that it's increasing, it's wasting like kind of resources for the BUCH. Now let's move to the next one, which is a dynamic codebook. Okay, again, for dynamic codebook, actually, if you look into this figure, the figure in the top here, this was the problematic figure which I showed in the previous phase. That, for example, if here the BTS sent TX, and DTX here, and because this one dynamic, so that you know that he should send nothing here, but the next transmission was being missed, not received, so the user also will not send anything here. The next one was being acknowledged, so the user responded, so the unit B will think that this acknowledgement is for this TX or this slot, not for this slot. This is where from the conflict is coming. So there should be something to let the user know this transmission for which slot. There is something called, and this is where something called DAI, okay, downlink, it's called downlink assignment index, where it's telling him, it will inform the user this transmission for which, for example, slot. For example, here you can see there is something added called CDI, counter DI, again downlink assignment indicator. For example, this telling him C1 TX, this is for C1. This means this is the first transmission. Then again, acknowledgement, he will know this one for C1, so he will be able to send the feedback as an acknowledgement for C1. Then C2, then DTX here, okay? Then he didn't receive it, okay? So he didn't receive C3. Then he received C4. So he will understand that he missed C3 because he received directly C4. So in this case, he will be able to send a non-acknowledgement because he will tell the Junubi, I didn't receive C4, I received directly, I didn't receive C3, I received directly C4. So please report again the C3 through sending non-acknowledgement here. So this will avoid this kind of conflict. And again, this is through something called downlink assignment indicator, CDI. And in case of multiple carriers aggregation, there is something addition on top of that one called total DI. Which is help you determine total number of downlink assignment. So both of them work to identify which transmission was being missed, both of them together. And again, this is very, very much better compared to the static one, because this is like saving a lot of resources here, and instead of having a fixed resources and limitations. So this one reduces overhead and can save the uplink resources by avoiding this kind of fixed size feedback. And this is actually also adaptive feedback. So it can also, if you have many carriers and many transport blocks and you need a lot, so it can increase the resources for that part. So it's working in an adaptive way, increasing the resources of BUCH whenever required, using it whenever also it's not required to send any kind of feedback. So from the network capacity perspective, this is very good. You need to check this one in your network, in your vendor, the capability of the device, whether it's supported or not, as I will show you how to do that in the next slide. So this slide, as you can see here, from Trace's perspective, again, you will go to the UE capability message. From the UE capability message, you will look for the physical parameter common. Under that one, you find that it's a dynamic HARQ, static, semi-static HARQ, and so on. Okay, so we'll find whether this one is being supported and on, and same for this another device and so on. Here, from the GNB side, there will be, I don't have like kind of traces for that, but from GNB side, from the UE, it will deriving under our serial configuration message telling them you are going to be using the semi-static or dynamic. It will tell the user. So this kind of network configuration. So we'll find, for example, from the traces, as I give an example, I give it manually here, PDCH HARQ Codebook, for example, telling them you are going to use dynamic Codebook. So this is giving more flexibility and can improve your BUCH capacity. So this is something actually very, very useful for the network. Now let's move forward to see what you have additional. Actually, this is additional feature, which is also can be very good for the BUCH capacity improvement. This is a very good one called spatial bundling, for example, as you can see here. Actually, the main idea of that part, if you remember in the previous one, when we were showing the example of two transport block, the user send two different acknowledgements, right? The user send two different acknowledgement to two different acknowledgement to the uplink, right? Two acknowledgement. That's why it's increasing. Kind of you have more carriers or you have more transport blocks, so you need to send additional acknowledgement. I did a correction here, but let me explain. So initially, without the special bundling or without this feature, okay, what would be the scenario? As we explained before, you have, for example, transport block transmitted here and one here and two here. Two transport block whenever you have, for example, let's say rank 5 or 6 or 7 or 8, and you have, for example, two transport block need to be transmitted. So the user, the UE feedback should be sent separately for each transport block. So you need to send two acknowledgements, one for the transport block 1 and one for transport block 2. This is a normal case scenario without using this feature. And this is in case of this feature is being used, he can send one acknowledgement to acknowledge both of transport blocks. Okay, so for example, if you look into that part in the bottom figure here, that initially the user will check the HARQ acknowledgement for both transport blocks. If he found that both transport blocks being received and both of them are positive, then he will send a single positive HARQ ACK, as you can see here. Just a single one, not two. So this will give a significant improvement in terms of the uplink overhead, okay, for the BCH capacity. But the drawbacks of that part, or a potential drawbacks, in case if one of them only is being failed and the other one is being successful, so since not both of them being acknowledged, so you will send a negative feedback, one negative feedback, telling them that please retransmit both of them. So this will increase the retransmission volume, because at the end, in case the transmitter was need only to retransmit one of them, it will be transmitting that both of them, even if only one is being failed. And this is the potential drawback. So this feature, for example, can be very useful in the scenarios where you know that you have a perfect coverage. Let's assume you have indoor coverage, indoor sites or event site where you know that coverage is granted, and there is no like very low error in the site and so on. So you can enable for that part for the events to improve the capacity point of view, because you are not worry about the user, for example, will have multiple errors and so on. So it's better to do this kind of bundling to improve your uplink capability. But again, this is again same scenario, require a U capability, special U capability called spatial bundling HARQ supported, and also to require the capability from the network itself for both even BUCH or BCH to make this kind of bundling. And this is very interesting feature as I mentioned. Next part actually will be the last part of this session, which is a quick comparison between 4G and 5G. Actually here, this is a quick comparison. The first part related to the HARQ synchronization time. I believe you will already, if you already have a familiar with 4G, you will know that there is something called asynchronous and synchronous HARQ. Okay, and 4G used to support asynchronous HARQ and uplink, asynchronous and synchronous and downlink. Okay, while in the 5G supporting asynchronous HARQ in both of them. I think this was the opposite way around, downlink and uplink. It was being reversed. I just corrected. It should be synchronous in uplink and asynchronous in downlink. And in 5G, it's having both asynchronous. What it means by asynchronous? Very simple. Simply, it means like as you can see in this figure, synchronous HARQ means that the time of the feedback is known by the user. He know when he will send. For example, here first transmission here, you know that he needs to send it after three slots. Same fixed time. So he know in advance when he should send the feedback. So for example, this doesn't have any flexibility. So for example, this can increase your HARQ transmission because in case if the user the send here, so you need to send acknowledgement or non-acknowledgement at this particular after 3 milliseconds or 4 milliseconds and so on. But in the asynchronous, as you can see, it can be any time after one slot, two slots, three slots, and so on. This is flexible, so giving flexibility for the retransmission. In case of doing retransmission after 5 or 8 milliseconds, can do it, for example, in 4 or 3 or 5 milliseconds. So this is actually the main differences between both of them. Okay, HARQ processes, as you mentioned, it increased from 8 to 16. I highlighted that before, and this is giving more advantage to have multiple transmission at the same time without waiting for the first or second or whatever to be acknowledged and so on. So this can increasing your data rate. For actually ACK and NAC for the BCH, in case of uplink transmission, and 4G used to send explicit feedback for the uplink data and the BHICH channel, if you remember, ACK or NAC. While in the uplink, we don't need actually. There is no explicit ACK or NAC because at the end, both of them are in the same node. Okay, the GNB and DB. So the GNB will only send a feedback whenever it's needed as a non-acknowledgement requesting for retransmission. For example, in the BDCH, whenever it's needed. Okay. HARQ Codebook, this was more simple in the 4G, and you will use to have kind of a fixed number of bits and so on. While here it's kind of complex, as we explained before. Uh, the HARQ feedback modes is supporting, for example, the CBG. Okay, redundancy version almost the same, no major changes in the redundancy version. Uh, this one have more granularity. This is almost the same part as the CBG. This is just kind of repeating here. And the HARQ timing, this was kind of fixed special DVDD, whenever you're going to send the feedback and the uplink, while this one is kind of dynamic and more configurable for the network, especially for the uplink as you highlighted, and also downlink. And the retransmission handling, this kind of in 4G was reaching up to 8 milliseconds because it's having a fixed slot boundary. While the retransmission now is flexible, so it's having much faster retransmission. And for sure, the self-contained is not our scenario now, but self-contained can happen within the same slot even, but it requires a super UE capability. And the most important part about the UE processing time. In the 4G, for example, the capability of the device was up to 2 milliseconds, even higher, sometimes less for sure, but let's assume 2 milliseconds. Now, as I showed you in the table before in the previous slides, now it can be even less than 1 millisecond. And this was the last part of today's session about the differences between 4G and 5G. I hope if you like the video to click like and comment and to spread the word and share it with your friends. Thank you very much and see you in the next video.